The first talk is by Yuriy Polyakov, and it's on OpenFHE, open source fully homomorphic encryption library.
Thank you, Ben. So I'm Yuriy Polyakov with Duality Technologies, and I'm a lead of the OpenFHE project. So this talk will be slightly less technical than the prior two talks, but hopefully it'll be exciting. So I'll say a few words about the OpenFHE project. I think many are already familiar with it. I'll try to be relatively quick in this part. But the high-level idea behind building OpenFHE was to introduce a library that incorporates several ideas from prior FHE projects, such as Palisade, HLEAP, OpenFHE, and FHE. And we were also trying to tackle certain design challenges that the prior projects encountered. And with this in mind, we are trying to build OpenFHE in a certain way and following certain guidelines. And from the cryptography perspective, we assume from the very beginning that all schemes that are implemented will at some point or already support bootstrapping and scheme switching. We see it as very important because some schemes can be great for certain applications or for certain functionality, and we may need to switch to others. Then the second part that's extremely important is the hardware acceleration. So we know there are a lot of efforts right now in building accelerated hardware cards, hardware acceleration cards. And in OpenFHE, there is a concept of a hardware abstraction layer where we're trying to provide an abstract interface so that different hardware backends could be built. And from the usability perspective, there are two important considerations. One, we're trying to make it as user-friendly as possible. So FHE maintenance operations such as modular switching, key switching, they are in the default modes, they're done automatically, and the developer of an FHE application hopefully should not be concerned with those unless the goal is to optimize it. At the same time, we are providing some support for more advanced modes where the developer or compiler can fine-tune those and when to use them. And a couple of key facts about OpenFHE. So the current version is 1.2.4. And as I mentioned previously, the OpenFHE started as an effort from co-authors of multiple libraries in the past. And we are also considering OpenFHE as an official successor of Palisade, the prior project. The implementation itself follows the homomorphicencryption.org post-quantum security guidelines and certain parameter settings. And the library is offered under the two-clause BSD license. So the idea is anyone can use it for any purpose, be it commercial or academic. This is our strong belief. And a lot of the initial support came from DARPA for the project. Also, ARPA-H is actively supporting this project. And we see it as a community library. So although, of course, Duality is involved in this project, there are many contributions coming from other organizations. For instance, Intel is now making a major contribution in the upcoming 1.3 release. And something to note that OpenFHE is one of the NumFocus projects. A lot of other like Python projects, such as SciPy, Jupyter, NumPy, are also in the same stable. And in terms of cryptographic schemes, OpenFHE supports, I would say, all relatively mature common FHE schemes. Of course, new schemes are being proposed, and we saw it in the first talk, for instance, but BFE, BGV, CKKS, and 3 flavors of FHE TFHE are currently available in the library. And the 2 most efficient TFHE variants, one, of course, is the CGGI TFHE, and the other one is the LMK Plus or LMK CDY variant that was described in the Eurocrypt 2023 paper, which seems to be even more efficient in some ways. And OpenFHE also provides threshold FHE capabilities for BGP, BFE, and CKKS schemes. It provides interactive bootstrapping for CKKS when threshold FHE is available. Also, proxy re-encryption based on key switching is available functionality for all SIMD schemes. In terms of scheme switching at this time, we have support for CKKS to FHE, with the idea that operations such as comparison or LUT evaluation can be done in FHE. We have, in our plans, we're going to add more scheme switching mechanisms. And again, at a very high level, the main idea of OpenFHE, I would say one of the main ideas, is to try to be inclusive, try to include various schemes, various capabilities, leaving it up to the developer, the user, to choose which scheme works best for their application. And so again, we try to incorporate some of the functionalities from the prior projects. There is still a gap as compared to HELEAP in terms of BGP, BFE bootstrapping, where we know this field is still unstable. There are many improvements being made, as we saw earlier today. But in general, everything that's quite common is being included. And from the perspective of the community, we try to, one way to look at OpenFHE, we're using a layered model where one could develop different hardware backends for OpenFHE without being concerned about the crypto schemes that these backends would be used for. So the crypto capabilities would be let's say, implemented in this core OpenFHE. And when someone adds, let's say, a GPU-based or FPGA-based functionality, they need to be primarily concerned with polynomial arithmetic and so on. And while OpenFHE itself is developed using C++, there are other interfaces available. For instance, Python interface is very common right now. There is a Rust interface. There is even a Julia interface that the community built, and various capabilities are either available or being built, and in this case, dashed lines correspond to projects in progress. The solid lines correspond to something that OpenFHE provides already now. And again, from I mentioned the layered model. From the contributor perspective, the goal, the hope, wherever we can achieve it, is to provide a mechanism for specialists in hardware acceleration to work on building the acceleration card for a certain arithmetic, experts in crypto capabilities to build certain new schemes or either prototypes or even add new ones. We're trying to provide, to support a modular approach. And one of the, I would say, key goals of this talk is to give an update on various, I would say, applications that OpenFHE has been used for. And before this talk, I spent some time just looking at various papers or various repos that are based on OpenFHE, and I tried to provide some initial systematization, trying to give us an idea of which schemes are used for what, and we're going to present some results here. And as part of this effort, so we added awesome OpenFHE to keep track of various applications, publications, tools based on OpenFHE. I'm sure a lot of references are currently missing there because we only started building this, but it should give an idea how OpenFHE is used. Also, there is a contrib repository where users can contribute their own projects, and the hope is that these certain higher level functionalities can be built by the community and shared with others. And so in this talk, as I mentioned, we'll try to do some initial analysis. It's very informal, but this is just to give an idea. So in these two repos, we looked at 39 application projects. Some of them are available in the contrib repository. Some are available in peer-reviewed conferences and journals. Some are even used for products. And we also looked at some preprint papers that are based on OpenFHE. So we'll start with applications based on BFE BGV, I would say it's a common knowledge that for solutions that deal with, I would say, relatively basic or maybe even more advanced PIR, PSI, private query functionality, BFE BGV-based approach is the most commonly used one in the industry. I mean, for instance, Duality, it has a product based on it. There are other solutions. I mean, there is APSI. We know that with leveled computations, with a relatively small depth, BFE BGV can solve many private query problems. So definitely a good use case for BGV BFE that is also illustrated by some of the applications. So another example where BFE BGV are useful deal with the operations over finite fields. So whenever we need to do some operations over finite fields, in my mind, BGV BFE is the best tool, and an example, an open source example, is available for substring search. There are many other examples as well. So here I'm just choosing examples to give an illustration rather than exhaustive list. There are recent papers, so as I was looking through citations, I saw that there is an interesting paper on secure and scalable gene expression that uses BFE, and which was recently published in Nature Communications. That's also, and the link is provided in those two repos. I saw some also BFE-based applications for, let's say, biometric recognition under encryption. And something that also has got quite a bit of attention is the use of BGV BFE for LUT evaluation. So there was, for instance, a Fermat challenge that was solved using BGV BFE, using Fermat's theorem and some additional things there. There is also an interesting ePrint paper by Yangwu and the Sila team that built something based on BFE LUT functionality. So in my mind, these are some of the common applications of BGV BFE that we see. So now we're going to look a little bit more at, now we're going to look at CKKS. And I want to say up front that it's the most commonly used scheme for OpenFHE applications. We're probably like 3/4 of the works that I've seen are based on CKKS in some way or another. And maybe some recent ML applications that I saw there was an interesting paper in New Rips, which is a top-tier conference in that space that deals with the problem of encrypted data pruning using CKKS. There are quite a few papers on image classification. For instance, the paper I'm referring to here is based on ResNet 20 that were published in also International Journal of Neural Systems. Some capabilities for security inference were discussed in prior CCS work, and also just I want to mention that as part of the homomorphicencryption.org working group on use cases and benchmarking, there is a fetch by cosine similarity project that is also using some of the capabilities of CKKS. And quite a few applications that we've seen are in the healthcare domain. Again, this is just a small list representative where OpenFHE was used for the analysis of oncological data, for GWAS, and so on. And interestingly enough, for some of these applications, CKKS even outperformed certain MPC solutions in the past. And something to note, that although CKKS is seen as a scheme for machine learning applications or for real number arithmetic, and problems such as sorting, ranking are often not the strongest capability that CKKS provides. I did notice a recent Usenix 2025 paper where some very impressive numbers are obtained just using CKKS in like treating it as a matrix version and providing some numbers here. So the other, I would say, branch thread of schemes is so CGGI, LMK-CDY, often known as the TFHE schemes. So there, something to note is that a lot of prior projects based on OpenFHE focused on Boolean circuits, on converting various programs into Boolean circuits and then being able to execute them. So for instance, Google Transpiler, essentially, now I think Google Transpiler is being replaced by Google Hair project, which we'll have a presentation on next, provided a capability to implement various algorithms. And there are some examples in the OpenFHE repository showing how you can do BGP shortest path, how you can do Dijkstra's algorithms and AES evaluation algorithms using this approach. Also, we previously considered, we used all Bristol formats, which were quite common in the MPC world, to implement various circuits such as adders, comparators, multiplications, various crypto primitives, floating point operations like division, equality, multiplication. So we've seen quite a few cases where OpenFHE was applied this way. And something to also note, there are papers appearing based on the scheme switching capability that I mentioned. For instance, I want to note recent Intel work that used the CKKS to CGGI, LMK-CDY scheme switching to evaluate comparisons. So this is something that we've also seen. So this is a combination of CKKS and CGGI schemes. And I want to briefly mention what are we expecting in the upcoming releases of OpenFHE, just like a little bit of a teaser. So a big contribution is coming from the Intel team, which is the composite scaling CKKS RNS variant. The high-level idea is to uncouple the word size from the scaling factor in CKKS. So this makes it easier to support hardware accelerators, for instance, using 32-bit words to achieve much larger precision. It also enables much more efficient support of in-CPA secure modes, which typically require more than 64-bit arithmetic. So this is getting close. So we expect to release 1.3 with Flavio's team's help in April. And in 1.4, we're planning to add the functional bootstrapping based on CKKS, a method that we also discussed in the FHE.org forum. Earlier this year, the high-level idea is that these methods can achieve much higher throughput than the TFHE-style schemes. And for something like 8-bit LUTs, we see a throughput improvement by 3 orders of magnitude. So we're going to put some effort into creating a usable interface for this. And the main resources in OpenFHE are listed here. So the website and some of the repos that I mentioned. Of course, the slides will be posted afterwards and available. And thank you.
Hi, thanks for the great talk. I was wondering whether there is any roadmap for GPU support in OpenFHE.
Roadmap for what, sorry?
GPU.
GPU? So I'm aware of a couple of projects that are where GPU backends have been built. None of them have been officially released yet. So there are a couple of different groups that are working on this. Hopefully relatively soon, but I cannot give you an exact ETA. I am aware of several groups.
Because I talked to some people that they do GPU here in the poster session. They told me that the way OpenFHE, polynomials, and other things are structured is not very compatible with GPU. Is it correct, or?
I would, I think I would be happy to chat with those people, and if you could, you could
Okay,
introduce
I will
them,
point
we
you.
could have a
I will do the
discussions.
matchmaking.
So it's there. Of course, there are some challenges in general, for any library when we want to achieve speed ups and data movement and so on. But it's I think it's achievable. It's achievable, but with some, of course, effort.
Thank you.
Any more questions for Yuriy? I could ask one then, Yuriy. The hardware abstraction layer, does that target specific hardwares like FPGAs, or I'm showing my ignorance here, but
I would say the hope, the vision is to support different kinds. So, for instance, AVX 512 is already supported, and there are efforts. So, although they're not officially released for ASIC, I'm aware of FPGA projects, GPU projects, and the library is built in a way where this is abstracted. So, for instance, OpenFHE can be run without knowing that there is a backend of a certain kind. The abstraction is very useful, and from the usability perspective, it does bring about some challenges. How do we achieve the best efficiency? So this is something that is work in progress. So as more backends are being added, sometimes we push up this hardware abstraction layer a little bit higher, let's say in key switchings. But the goal is very ambitious to support any kind of acceleration that's being considered.
cool. Thanks. We have time for one more question if there is one. Okay, let's thank Yuriy again.